In January 1941, a Caltech physicist named R.M. Langer published an article in Popular Mechanics. He argued that uranium-235 could power cars, ships, and aircraft. The idea at the heart of the piece, a nuclear-powered flying wing, seemed like pure science fiction to readers and experts alike. Yet just a year later, Enrico Fermi, one of the pioneers of nuclear physics, was already talking through actual designs for a nuclear-powered aircraft with colleagues on the secret Manhattan Project. 2 years later, the Army Air Forces started taking the idea seriously. In the spring of 1946, together with the Manhattan Engineer District, they launched a joint effort called NEPA, short for Nuclear Energy, for the propulsion of aircraft. The goal was to find out whether a nuclear-powered plane was feasible at all. The order setting it up was signed on May 28, 1946, and the work was based at Oak Ridge, Tennessee, the secret city the Manhattan Project had built 3 years earlier. The military was looking for a strategic bomber or reconnaissance aircraft that could stay airborne for days at a time without refueling. But engineers ran straight into a wall of technical problems. They had to work out how radiation affected airframes and engine materials. They also had to weigh the environmental risk in normal flight and in a crash, shield the crew and the ground crews from radiation, and find a safe place to fly the thing. Every one of those questions came back to the same brutal arithmetic. A reactor light enough to fly would throw off a torrent of neutrons and gamma rays, and the only known way to stop them was mass, which happens to be the one commodity an aircraft cannot carry in unlimited quantity. In July 1947, the military laid out the first formal requirements for the aircraft it wanted. A takeoff weight capped at 300,000 pounds, a top speed of 515 miles per hour at 35,000 feet, and a payload of 12,000 pounds. And crucially, even in the worst kind of crash, the aircraft was not to raise natural background radiation in any meaningful way. The prime contract went to Fairchild. Fairchild's engineers looked at what radiation did to structures and to the airplane's electronics, and at how to keep the crew and the ground people safe. As part of that work, they flew a modified B-29 Superfortress with a live radioactive source in the bomb bay and measured what came through to the crew stations up front. But the job turned out to be bigger than Fairchild could handle. Work stalled on both the airframe and the engine, and the contract was canceled. By late 1948, Air Force spending on NEPA had already passed $10 million. Despite the money already gone, many of America's leading physicists were against the whole thing. Chief among them was J. Robert Oppenheimer, who chaired the Atomic Energy Commission's General Advisory Committee at the time. Oppenheimer thought a nuclear-powered aircraft was impractical on its face, and he warned his colleagues again and again about how dangerous the tests would be. The pushback pushed the AEC into asking MIT for an independent look in 1948. That work ended in a big scientific conference that brought the Lexington Project team together with everyone who had a hand in NEPA. In their final report, the experts concluded that a nuclear aircraft was technically possible, hard as it would be. They put the development at 15 years and $1 billion. The study weighed turbojets, ramjets, and rockets, and came down on turbojets as the best bet, whether direct cycle or indirect. In April 1949, after a key meeting, the United States Air Force and the Atomic Energy Commission threw out what had come before and started fresh with the Aircraft Nuclear Propulsion Program, or ANP. In 1951, they brought in 4 big defense contractors and set them against each other. General Electric and Convair took the direct cycle, where the reactor heats the air that goes through the engine. Pratt and Whitney and Lockheed took the indirect cycle, with a coolant loop in between. In May, the whole thing moved under a joint Air Force and AEC office. General Electric ran its half out of Evendale, Ohio, outside Cincinnati. Pratt and Whitney built an entire secret plant for its half at Middletown, Connecticut, the Connecticut Aircraft Nuclear Engine Laboratory, or CANEL. General Electric's power plant ran on the direct cycle. Intake air was compressed and fed straight into the reactor core, superheated there, and then run through the turbine. The layout was mechanically simple and quick to develop, and that was the whole appeal. It also had one flaw that never went away. As the air ducts inside the core wore down, the engine vented radioactive particles straight into the atmosphere. Engineers first planned to build the system around General Electric's J-53 turbojet. but the numbers came back at roughly 165,000 pounds for the whole nuclear installation. 97,000 pounds of that was shielding alone, more than an empty B-29 weighs, carried purely to stop radiation. To get the weight down, engineers switched to a proven production engine, the J-47 from the B-47 Stratojet. The version reworked to run on reactor heat was designated the X-39. The conversion was less an invention than an amputation. Engineers cut the combustion chambers out of the middle of the J-47 and replaced them with ducting, so that compressor air left the engine, traveled to the reactor, picked up its heat inside the core, and came back to drive the turbine. Airflow was cut back from roughly 100 pounds per second in a standard J-47 to about 70. Where a jet engine normally carries a flame, this one carried a reactor. Between 1955 and 1957, General Electric engineers tested various system layouts using purpose-built test rigs. They were called the Heat Transfer Reactor Experiments, HTRE-1, HTRE-2, and HTRE-3, and they lived far out in the high desert of eastern Idaho at the National Reactor Testing Station. The first rig was built simply to prove that a turbojet could run on nuclear power. It consisted of a reactor, radiation shielding, 2 X-39 engines, ductwork, and control systems. On January 31, 1956, HTRE-1 did exactly that, running a jet engine on fission heat for the first time anywhere in the world. On the second rig, they tested different reactor core configurations. HTRE-2 was HTRE-1 rebuilt with a removable plug at the center of the core, so experimental fuel and moderator samples could be cooked under real conditions and pulled back out. The third setup became a full-fledged prototype for flight testing. On paper, it made enough thrust to push an aircraft along at 460 miles per hour, effectively forever. HTRE-3 was the one that finally looked like something meant for an airplane. Its core lay horizontally instead of vertically, its control rods worked sideways, and it used solid zirconium hydride as a moderator in place of water. It drove 2 X-39 engines at full power, and it demonstrated something nobody had managed before, starting a jet engine on nuclear heat alone. Radiation levels were still dangerously high. During one test, a control system malfunction vented radioactive material into the air and contaminated the test site. Meanwhile, Convair was developing its own supersonic airframe under the X6 designation as part of the ANP program. The paperwork went back to September 5, 1951, when the Air Force contracted with Convair under the project code ASHI MX-1589. That contract covered 2 airframes. One would carry a reactor aloft purely to measure radiation and prove out shielding. The other would become the X6. They evaluated both tailless delta and canard configurations. The aircraft was projected to have a maximum takeoff weight of up to 165,000 pounds. As a baseline, they took the B-58 Hustler, then still on the drawing board at Convair. The X6 was designed to take off and land using conventional jet engines, with the nuclear power plant taking over during cruise flight. The nuclear propulsion system put a reactor in the rear fuselage driving 4 X-39 engines. Different design studies hung those engines either above or below the fuselage, close to the reactor. The conventional turbojets went on wingtip pylons, and for safety, the crew compartment was pushed as far forward in the nose as it would go. Full shielding all the way around weighed more than the aircraft could carry, so engineers had to compromise. They went to shadow shielding, sometimes called divided shielding, cutting the shield back until the whole installation was light enough to fly. The logic was blunt. Rather than wrapping the core in a sphere heavy enough to protect every direction at once, you put the mass only in the cone between reactor and cockpit and accept that radiation streams out freely everywhere else. Everything outside that shadow, including the ground crews, is somebody else's problem. The crew compartment itself was a heavily shielded capsule. Directly behind it, engineers put a bulkhead filled with borated water, which is very good at soaking up neutrons. Ground crew safety after a nuclear flight was worked out in some detail. The X-6 would touch down with its reactor already shut down and be towed to a pad built for the purpose. There, the whole power plant would come out of the airplane, go down a deep shaft, and sit in a shielded bunker underground until the next mission, Nobody would service the airplane with a hot reactor still in it. The first X-6 flights were penciled in for 1956. Those flights never happened. In 1953, the incoming Eisenhower administration went through the defense budget line by line, and an experimental aircraft that would cost a fortune and carry no bombs was an obvious place to cut. The airframe half of the program was canceled on cost grounds. What survived was the other half of that 1951 contract, the flying testbed. Shadow shielding had to be tested in the air, not on paper. For that, there was one obvious airplane, the heaviest bomber the Air Force had, the B-36. The B-36 spanned 230 feet, the longest wingspan of any combat aircraft ever built. 6 Pratt & Whitney R-4360 Wasp major radials, 28 cylinders apiece and roughly 3,800 horsepower each, faced backward along the trailing edge as pushers, and 4 General Electric J-47 turbojets hung in pairs beneath the outer wings, about 5,200 pounds of thrust each. Crews had a phrase for the sound of all 10 running up on takeoff: 6 turnin' and 4 burnin'. 384 Peacemakers were built, every last one at Fort Worth, Texas, in a government-owned plant known as Air Force Plant 4, whose main assembly building runs very nearly a mile end-to-end. 83 of those aircraft were H models. It grossed out at over 410,000 pounds, better than 200 tons. It could haul 86,000 pounds of bombs. In May 1953, one of them was picked for conversion, an airplane already sitting in the shop at Fort Worth, torn up by a tornado at Carswell Air Force Base the previous fall. Without that tornado, there is probably no flying nuclear test bed at all. It crossed the Carswell flight line at around 6 in the evening on September 1, 1952, with winds measured at 91 miles per hour and gusts to 125, and it was gone again in about 10 minutes. When it passed, 106 B-36s were damaged, better than half of Strategic Air Command's entire heavy bomber force. General Curtis LeMay pulled the Air Division at Carswell out of the war plan. The one piece of luck was that Convair's plant sat directly across the runway from the base. The repair effort was christened Project Fix-It, budgeted at more than $48 million, and the last damaged aircraft went back to the Air Force on May 11, 1953. The airframe chosen for the nuclear work was a B-36H-20CF, serial number 51-5712. It was already at the plant, already torn open, already paid for, and never going to serve as a frontline bomber again. For a while, the Air Force carried it on the books as the B-36H. In the rear of this flying testbed's bomb bay, engineers installed a 1-megawatt experimental reactor, 1 thermal megawatt, since it made no electricity at all. It was called the Aircraft Shield Test Reactor, ASTR for short, and the name is the point. It was a source, not an engine, never connected to the aircraft's propulsion and never producing a pound of thrust. Its job was to make radiation, so instruments up forward could measure what got through. It was about 4 feet across, weighed nearly 35,000 pounds, and burned uranium dioxide. The reactor was only ever brought up to power in flight. It was cooled by outside air, rammed in through scoops cut in the sides of the fuselage, run through the reactor, and dumped overboard. Nor was it bolted in. It hung from a hook in the bomb bay, so the whole assembly could be winched up into the aircraft before a mission and lowered back out after one. To keep the crew alive, Convair built a shielded capsule into the nose, weighing over 26,000 pounds. Its walls were lead and rubber. The cockpit windows were leaded glass close to a foot thick. Behind the cockpit sat a slab of steel and lead over 6.5 feet across and 4 inches thick. Gone was the B-36's greenhouse nose with all its framing, and in its place sat a squat, blunt, faintly armored snout pierced by small ports. 9 water-filled tanks were spread through the fuselage as well, water being an excellent absorber of neutrons and, unlike lead, free. In flight, the crew watched the reactor from the cockpit on closed-circuit television. A parallel effort with the memorable codename Project Halitosis sampled the air around the aircraft for radioactive gases. And at the Convair test facility in Texas, there was a shielded pit in the ground that bracketed every mission. The bomber was positioned over it, the reactor lowered away into the ground on its hook, and the aircraft towed off, having left the radioactive part of itself behind. Crews and paperwork alike started calling the converted bomber the NB-36H. It first flew on September 17, 1955. 5 men flew it, a pilot, a co-pilot, a flight engineer, and 2 nuclear engineers because the most important system aboard was one. No pilot had been trained to operate. The regular crew was A.S. Witchell, known to everyone as Doc, in the left seat, L.C. Brandvig in the right, and J.D. McEachern as flight engineer, with James Nance and Steve Andrech running the reactor from a console inside the same shielded compartment. Every flight stayed over empty country in West Texas and New Mexico, and the NB-36H never flew alone. A transport tagged along with a squad of armed Marines aboard. If it went down, they were to jump in and secure the wreck before anyone else got to it. A Boeing B-50 flew chase as well, rigged out to map the radiation field around the bomber in the air, and the reactor was brought up to power only once the aircraft was clear of anything that could be hurt. In the fall of 1956, the designation became official. The airplane made its final flight in late March 1957, 47 test flights all told. Those flights added up to 215 hours in the air, and the reactor was live for 89 of them. 89 hours is still the sum total of American experience with a live reactor in the air. As it turned out, the whole program ran without a serious incident. The shielding worked in the narrow sense that the men in the nose were adequately protected. What no amount of flying could answer was the question Oppenheimer had been asking since 1948. What happens on the day one of these comes down? In late 1957, the NB-36H was retired. Meanwhile, Pratt & Whitney was working its own end of it, the indirect cycle. The big advantage was that the engines didn't throw radioactive exhaust out the back. They got there by adding a closed water loop that carried the heat away from the reactor. In that primary loop, a 49,000 horsepower steam turbine drove a 10-foot fan in a second open loop. Outside air pulled in by that fan ran through the turbine condenser, heated up, and blasted out a nozzle as thrust. It quickly became clear that the ducted fan was inefficient and the whole system too heavy. So in 1953, Pratt & Whitney built and tested a second version, 1 reactor, 6 J91 turbojets, each of them over 25,000 pounds of thrust. Liquid sodium did the cooling in a closed primary loop, handing its heat through an exchanger to the air in the secondary loop. That shaved nearly 44,000 pounds off the reactor and its shielding. The old problem stayed, though, a complicated heat exchanger and all the plumbing it took to move liquid metal around an airplane. The materials problem underneath all of it was being worked back at Oak Ridge. In November 1954, the laboratory brought up the aircraft reactor experiment, a 2.5 megawatt design whose fuel wasn't solid at all. It was dissolved in a molten fluoride salt that circulated through the core. It ran for over 200 hours at temperatures near 1600 degrees Fahrenheit, the first molten salt reactor ever operated anywhere. Built to answer an aircraft question, it ended up answering a different one and led directly to the molten salt reactor experiment. Pratt & Whitney got a reactor of its own running at Oak Ridge, too. PWAR-1 went critical on February 5, 1957, at essentially zero power and near 1250 degrees Fahrenheit, purely to check that its circulating fuel behaved the way the calculations said it would. But the company never produced anything that could be hung on an aircraft. 15 years of indirect cycle work at Middletown yielded high-temperature alloys, liquid metal pumps, and a great deal of hard-won metallurgy and no flight engine. In the end, the lab went back to Pratt & Whitney to build ordinary jet engines. By then, the requirement itself had begun to dissolve. In March 1955, the Air Force wrote out what it actually wanted in a document called General Operational Requirement 81, the ancestor of what became Weapon System 125A. It asked for a nuclear bomber with something like 10,000 nautical miles of range, which is most of the way around the world, cruising between 60 and 75,000 feet, capable of staying up for a week or more, in service by 1963. Convair and General Electric went at it from one side, Lockheed and Pratt & Whitney from the other. Within about 2 years, the Air Force concluded that no such aircraft could be made into a useful strategic weapon at an acceptable price and canceled the requirement. General Electric kept building anyway, Its intended flight engine, the J-87, was designed as a genuine production turbojet driven by a production reactor, and two of them were eventually run up to nearly full thrust on nuclear heat in Idaho. By that point, you could make a fair case that the engine problem was solved. What killed the program was never the engine. It was everything wrapped around it, and above all, the calendar. In September 1959, the first Atlas intercontinental ballistic missiles went on operational alert. A missile could put a warhead on the far side of the world in half an hour, with no crew, no shield, no reactor pit, and no possibility of scattering a hot core across somebody's farmland. The nuclear bomber's selling point had been endurance measured in days, and that answered a question the Air Force had stopped asking. On March 28, 1961, the Kennedy administration wrote the program out of the budget. The message to Congress put it about as bluntly as a budget document ever does. 15 years, $1 billion, and still no realistic prospect of a militarily useful airplane. $35 million was left in place for Atomic Energy Commission research, and that was it. Development stopped. The Lexington Report of 1948 had predicted 15 years and $1 billion. It was almost exactly right about the time and the money. Its only mistake was assuming that at the end of it all there would be an airplane. The aircraft itself did not survive to see the cancellation. In 1958, the reactor was pulled from the NB-36H for the last time and driven to Oak Ridge in a convoy that spent 44 hours on the road. There, it was hoisted 186 feet into the air at the tower shielding facility, so shielding could go on being measured without an airplane around it. The airframe stayed behind. In September 1958, the only aircraft the United States ever flew with a working nuclear reactor aboard was cut up for scrap at Fort Worth, on the same field where it had been built and rebuilt. Not one piece of it was preserved. The reactor outlived the airplane by decades. It came back from Oak Ridge to Fort Worth and was installed for good at what became the Nuclear Aerospace Research Facility, where the reactor itself was redesignated the Aerospace Systems Test Reactor. It was uprated from 1 megawatt to 3 in 1959 and to 10 megawatts in 1963, and spent years irradiating materials for programs that had nothing to do with nuclear flight. The Idaho hardware outlived everything. When the money stopped, the heat transfer reactor experiments were left standing in the desert. In December 1988, HTRE-2 and HTRE-3 were hauled 31 miles south to Experimental Breeder Reactor 1, the reactor that first lit a string of light bulbs with atomic power, by then a public museum. They sit outdoors there to this day, two weathered slabs of steel and shielding the size of small buildings, as close as this program ever came to a monument. The B-36 itself bowed out at about the same time. On February 12, 1959, the last one in Air Force service flew from Biggs Air Force Base in El Paso to Amon Carter Field in Fort Worth. Named City of Fort Worth for the place that built it, that machine survives today at the Pima Air and Space Museum in Arizona. So this is what 15 years and $1 billion, call it 10 or 11 billion in today's money, left behind. A handful of peacemakers in museums, 2 reactors in a parking lot in Idaho, and 89 hours of flight time with a live pile in the bomb bay. The X-6 was never built. No aircraft anywhere has ever flown under nuclear power. The Soviets ran the same experiment with the Tu-95 LAL, flying a reactor 34 times in 1961 without connecting it to anything, and gave it up for the same reasons. The shielding a human crew needs weighs more than an airframe can afford to carry, and no amount of clever engineering has ever persuaded a neutron to take an interest in the weight budget.